So Leonardo of Pisa is well known for the Fibonacci sequence, but in his book Liberace, there were several other problems and some techniques for working with arithmetical structures of the time. And today what I'd like to do is look at two more problems from this book, or I guess I should say one problem and then one algorithm for rewriting fractions as quote unquote Egyptian fractions. And before we get into this, I'd like to thank the sponsor of this video, DataCamp, but we'll talk about them more later. Okay, let's jump into this first problem. So what does it say? It says that a lion can eat a sheep in 4 hours, a leopard can eat a sheep in 5 hours, and a bear can eat a sheep in 6 hours. How long will it take them to eat the sheep together? So in other words, if you give all three of these animals a sheep and they share nicely, how long will it take them to eat the sheep? So this is a play on a puzzle that floats around the internet quite a bit. And while this type of problem is common, what's nice about this one in particular is it dates to the 1200s, so the 13th century. Okay, so let's maybe see how a solution might go. Well, let's look at these numbers 4, 5, and 6 and find their LCM. So let's notice the LCM, or the least common multiple of 4, 5, and 6 is equal to 60. Now you might ask, why do we want to do this? Well, this is the best way to compare the speed of the lion, the leopard, and the bear. And how can we use this 60? Well, we can look at how many sheep each of these animals can eat in 60 hours. So let's write this down. In 60 hours, what do we have? So the lion eats how many sheep? So if it takes 4 hours to eat one sheep, in 60 hours it can eat 15 sheep. So here this is 15 sheep. And then we can play the same game for the other ones. So the leopard, how many sheep does it eat? Well, that'll be 60 divided by 5 in this case, which is 12. So the leopard eats 12 sheep. And then finally, the bear will eat 10 sheep. And so that's because it takes the bear 6 hours to eat a single sheep. So kind of obviously in 60 hours, it can eat a total of 10 sheep. So now let's put all of this together and notice that in 60 hours, they eat how many? Well, it's going to be 15 plus 12 plus 10, so 37 sheep. Okay, nice. But now with this information, it's fairly easy to produce a solution to our final goal, and that's just by taking the quotient of 60 by 37. So in other words, it takes 60 divided by 37 hours. So how many hours is that? That's approximately 1.62 hours to, I'll just put share one sheep between the three of them. So like I said before, this is a well-trodden problem, but what I think is nice about it is that it dates back to the 1200s, like I said before. Okay, so let's get rid of all of this and we'll look at an algorithm developed by Leonardo of Pisa in order to write fractions in their so-called Egyptian form. I'd like to thank DataCamp for sponsoring today's video. DataCamp is an online learning platform that offers over 350 data science courses at all levels, beginner to pro. DataCamp even has a free assessment tool to get you started at the right level. Coding and data skills require the same sort of careful argument as proofs in pure mathematics, like we do on this channel. As such, this is an excellent companion skill for learning mathematics, or anyone who loves mathematics. Personally, I'm finally getting around to learning how to code in Python. This is like part of a broader goal for me to implement a computational tool for my own research, as Python is used widely in mathematical research, including pure mathematical research. DataCamp has really accelerated my learning process of Python. So I'm pretty excited about that. Unlock new career opportunities and become data fluent today. Use my link in the description box below and check out the first chapter of any DataCamp course for free. There's a link in the description. And another big shout out and thanks to DataCamp for sponsoring this video. So the next bit of mathematics from Leonardo of Pisa, in other words Fibonacci, that I'd like to talk about today is his method for rewriting fractions as we would write them today in terms of their Egyptian form. Now, before we do that, let's recall what the Egyptian form of a fraction is. So an Egyptian fraction is a sum of distinct fractions with numerator equal to 1. So as a very, very simple example, the number 5/6 can be rewritten as 1/2 plus 1/3. So that's the sum of two fractions that are distinct and have a unit numerator. In other words, the numerator is equal to 1. Okay, so the algorithm that Fibonacci came up with, which I think is sometimes called Fibonacci's algorithm, goes as follows. So if we want to take the fraction x over y and rewrite it in its Egyptian form, we would do the following process. We would write 1 over the ceiling of y over x plus negative y mod x. So that's the reduction of negative y modulo x, obviously, taking the positive residue over y times the ceiling of y over x. And then this object right here will likely not have a numerator of 1 unless you're at the end of the process. So that being said, you need to iterate this until everything kind of comes out with a numerator of 1. Okay, so let's look at a nice example. Let's take the number 21/32 and expand it using Fibonacci's algorithm. So let's notice that the first thing that we would do is write this as 1 over the ceiling of 32/21. And then that'll be plus negative 32 modulo 21 over, let's see, we'll have y, the role of y is being played by 32 in this case, and then the ceiling of 32/21. Okay, so we've got something like that working. Now let's reduce this minus 32 mod 21 and see what we get. So we can do that easily just by adding multiples of 21 until we get a number between 0 and 20. But then you'll see if we add 42, which is 21 times 2, we'll get the number 10. So that means this thing right here can be replaced with 10. Okay, nice. Another thing that we'd like to notice is that 32/21 is between 1 and 2. So when we take its ceiling, we get 2. Furthermore, when we take the ceiling here, we also get 2. But that gives us a little bit of simplification. This 2 will simplify this down to the number 5. So that means at the moment we have 1/2 plus 5/32. And now we reiterate that starting with this 5/32. So let's see what that'll look like. So now we'll have 1/2 plus, so this will be 1 over the ceiling of 32/5 plus minus 32 mod 5. That's what's occurring in the numerator. And in the denominator, we'll have 32 times the ceiling of 32/5. So something that looks like that. But now we need to do a little simplification. So we can add multiples of 5 until we have something between 0 and 4. We'd probably like to add 35. That will give us the number 3. So we can replace this with 3. And then likewise, 32/5 is between 6 and 7. So if we take the ceiling, we get the number 7. Same thing here, we get the number 7. And then we've got 32 times 7 in the denominator. We can't cancel that with anything in the numerator. So we're kind of building up to a fairly large denominator here. In fact, in this case, we're going to have 1/2 plus 1/7 from this term plus 3/224. Okay, so that's where we are at the moment. Now let's do another step. So this is going to give us 1/2 plus 1/7 plus, and now we do the process again on that 3 over 224. So that'll be 1 over the ceiling of 224 over 3. So that's what we start with. And then plus negative 224 modulo 3. And then finally, this is going to be all over 224 times the ceiling of 224 over 3, like that. Okay, nice. So let's see. So this 224 over 3 is between 74 and 75. So that means when we take the ceiling, we get 75. So that's there and there. Another thing is we need to reduce this mod 3. This actually reduces to 1 mod 3. And how could we check that? Well, we could sum these digits. 2 plus 2 plus 4 is equal to 8, but 8 is 2 mod 3, but we've got a minus sign, and then negative 2 mod 3 is 1 mod 3. So we've got a 1 there. But look, now we've got all numerators of 1. We have 1/2, 1/7, 1 over 75, and then 1 over 224 times 75. So putting this all together, we have our final answer. So we've got a 1/2 plus a 1/7 plus 1 over 75, and then multiplying this last thing out will give us 1 over 16,800. And so that's the Egyptian fraction decomposition of 21 over 32 using Fibonacci's algorithm. And that's a good place to stop.